How to solve a recurrence formula involving infinite series and summation is explained and illustrated in this example. A sequence with general term an is given to us with initial term a1 equal to 6 as is highlighted here. So that's the initial term of the sequence. And with a recurrence formula that says the general term an is equal to 2 times the previous term an minus 1 plus 2 times index n. If we use this formula recursively, we can find that A2 is 16, A3 is 38, and A4 is 84, and so on and so forth. But that's not the purpose. We are not trying to find the numerical values of these terms. What we want to find is we want to prove that it's possible to use this recurrence relation and figure out the closed form formula for the general term an purely as a function of the index n, as we can see, 6 times 2 to the n minus 2 times n minus 4, valid for any index greater than or equal 1. Okay, so let's prove this. Generally speaking, the powerful tool available is either forward substitution or backward substitution. I am going to use forward substitution, and if in any of these examples forward substitution doesn't work, then we can use backward substitution. So, all right, so here is the use of forward substitution, and naturally it involves starting from the initial term a1 equal to 6. So I'm not going to write it again. We know that's a1. But maybe as a reference, we just write it here so that it's always available. Okay, so next term obviously is the a2. So I am going to write a2 equal to, and I just use the formula that is given to me. So a2, when we assume that index is n equal to 2, then naturally becomes equal to 2 times a2 minus 1, so a1 plus 2 times 2. Let's not replace or substitute a1 with 6. We know its value is 6, but let's keep it as it is. So in this sense, I am going to write is 2 times a1, and then we have plus 2 times, and then we have 2. Okay, so let's refer to this as equation 1. Now let's keep doing this one more time. So A3, now our index of focus is 3, so we can use the same thing. This time in the formula, we have n equal to 3, so naturally it is 2 times A3 minus 2, which is A2, and then 2 times 3. Okay, so let's exactly substitute 2 times A2 plus 2 times, and then we have 3. Okay, so what I'm going to do now as a next step, I am going to substitute A2 using information from the first line. So substitute A2 with this equivalent value. So if I do that, I can write this whole thing is equal to 2 times. That's this guy. And then for A2, I am going to substitute the value shown here. So copy paste. Okay, there you go. So that's for A2, and then we close the bracket, and then the rest of the equation should show up as well. So we have rest of them showing up. All right, just to do one last cleanup in the process. So basically what I'm trying to say, we found that A3 in equation 2 is equal to, so obviously 2 times 2 will give us 2 to the power 2. So I am going to write 2 to the power 2, and then A1 as it is. So A1, and we have 2 times 2, so will give us another 2 to the power 2, but this time multiplied by 2. So I am going to copy paste this guy. So write it here, and then plus and multiplied by 2. And finally, the final term should be there as well. So that's just copy paste. All right, remember that the final term has a power 1. Okay, so let's do one more time, and I think that's good enough to see the trend, because all we need to do is finding the trend so that we can extrapolate and find the formula for the general term. So if I do that, obviously for this one, similar to what we wrote for the top one. So I'm going to copy paste the top one, except we know that index should be corrected. So it will be index A3 now. So A4 depends on A3 and the last value is 4. Okay, so the same trick that we did before. Replace A3 with its equivalent, so which is this value. So I am going to write, therefore, this whole thing is equal to, again, 2 times bracket, and copy paste what we found before as a replacement here, and then close the bracket. That's the end of 2. And finally, we have the final term, which needs to be there as well, untouched. So I'm going to use the final term, and just if we do the final cleanup so that things are nice, we're gonna get, so same as before, 2 times 2 is 2 to the power 3, 2 times 2 to the power 2 is 2 to the power 3, but one of them multiplied by a1, the other multiplied by 2, and 2 times 2 is 2 to the power 2. So if I sort of speed up the process, I can just copy paste and make the correction live there. 2 becomes 3, 2 becomes 3. These guys are still valid. And then 1 becomes 2 for the power of 2, 3 is valid, and there is a one last term that should show up as well as before. So this last term should be there. Perfect. Okay, so we found in equation 3, and the trend is already obvious. We are chasing A4, so index is 4. Let me use a different color so that it is clear. So index is 4 in A4, and we end up with 3, 2, and 1. And as you can see, when we chase index 4, the last scalar is 4. And the previous scalars are 3, 2, and finally we don't have 1, but we have A1, which is 6. Okay, so I'm going to use this trend for the AN. So extrapolating from what we are seeing here, so ellipsis, basically I am saying, okay, let me just write A index N equal to. Okay, I know for that we have to end up, when it was 4, we had 3 in the power of the first term for the 2 base. So therefore we have 2 to the power and n minus 1. And then times A1. A1 is 6. So I don't worry about A1. I can replace it anytime later. Plus, again, the same thing. We have 2 to the power n minus 1. And this time we know it's going to multiply 2. So there is nothing unexpected there. And this will keep going on forever for a finite length though. So plus, let me just copy paste this whole thing. It becomes faster. So if I do that, then we have this term, but then this power should go down by 1. So instead of n minus 1, now it's n minus 2. And then the value inside the parentheses, so the value inside the parentheses will become 3. So 3. The previous one was 2. And we can write the rest of the process, I think, just a matter of maybe seeing the whole thing. So plus, there you go. The last one I'm going to write before another set of ellipses, n minus 3. And then we have 4. And plus dot dot dot, that's the ellipsis, because it's a finite series. It will end up with the last set of values. So what are the last set of values? So we get 2 multiplied by 2 to the 3. So that was when, so all I'm saying is this last one is n minus 2 instead of 2. This 3 will become n minus 1, and finally 4 becomes n. That's all we need to do. So I'm going to write 2 to the power 3 times n minus 2, and I am going to just copy paste this and make the correction for the rest of them. Make it easier. 1 and 2. That's it. Okay, so let's make the correction. So 2 to the 3 is already mentioned. Then the next one is, of course, 2 to the 2. And the correction needed is n minus 1. And finally, we have 2 times n. Done. This is the formula we were chasing. So if I can highlight it, in this formula for an, we have effectively sort of a closed form formula, not as neat as we wanted, because the target formula is what is written on top, this guy. We are getting close, but we are not there yet. Okay, so in this formula, what we can observe is, let's focus on the part that looks like have a trend, though seems like a complicated trend. So let's name this whole thing as sequence S, or at series S, sum S. It's a finite summation, but it's not, it doesn't look easy, but let's try a trick. So because of the nature of this finite sum, what if I try to compute 2 times S? So I am going to compute 2 times and then S equal to, okay, as simple as every term you see here, just multiplied by 2 for all terms. So naturally the first term here becomes, so just to make it faster, let me just copy paste all the terms involved in computing S and move them to here. Hopefully it would be proper spot. Not exactly, but it is fine. Okay, so there you go. Perfect. This name S can be moved here. All right, we have enough clarity. So here, what's the benefit? Well, let's make the multiplication. So naturally 2 to the n minus 1 becomes 2 to the n, 2 to the n minus 2 becomes 2 to the n minus 1, 2 to the n minus 3 becomes 2 to the n minus 2, 2 to the 3 becomes 2 to the 4, 2 to the 2 becomes 2 to the 3, and 2 to the 1 becomes 2 to the 2. Okay, fine. What else we can do? Okay, so let's rewrite it. I am going to do so. So let me just rewrite this portion. I'm not going to touch those two guys, those two terms. So 2s is equal to that one. What I'm going to play is a little game here. I'm going to play this game. So keep this one. Okay. One more time. Perfect. So now I am going to break 3 into 2 plus 1. So, and I'm going to change the color. 2 plus 1. That I can do. There is nothing wrong there. So basically what I did, I kept 2 to the n minus 1, and I said 3 is equal to 2 plus 1, and separate the terms. So basically factor, sort of distribute or factor out. Okay, so distribute 2 to the n minus 1 into the whole process. Let's do this for the rest of them as well. So if we keep doing this for the rest of them, so plus, and now the same thing can be done for the next guy, next term, which is this term. So copy paste, and in this process, repeat twice. Okay, now break it down. 4, write it as 3 plus 1, which is completely doable. Okay, and now let's not repeat for the part that is represented by ellipsis, and then instead do it for the rest of the terms. So I can do 2 to the 4 times n minus 2 as, there you go. So instead of n minus 2, I can write n minus 3 and then plus 1. Plus, for the next one here, okay, for this one, I can do the same thing. Okay, except instead of n minus 1, I can write n minus 2, and then I can do 1. And finally, I can just close the parentheses here. So there you go. And for last term, I can do the last stage here. So plus, and the last term, I am going to select this guy, and there you go. So for this one, remove the parentheses, remove the n, okay, and rewrite n minus 1 plus 1. There you go. So close, close. Now, one thing I'm missing, if you consider the original S, we have all the terms of original S except for the last term. So let's add that as well. So I am going to add it. There you go. But I added it intentionally. I need to subtract it. So I have to subtract that one as well. So there you go. I am subtracting it. Let me just make sure it is there. So plus and then minus. There you go. So I just added, subtracted these two guys. Nothing happened. So there is no further complication coming from there. But the beautiful thing is you can see what's going on. The trend we have in this summation here, when we are adding these terms, it's exactly S. So this is exactly S. As you can see, what is S? So what I found is, as one summary of the whole thing here, I found that 2 times, so let me just write it here. So 2 times S plus rest of the whole thing. Okay, so 2 times S is equal to, so I'm not going to touch these guys for now, but then I'm going to replace all the stuff that are sort of encircled with blue color shown as S. I'm going to write it as S. There you go. And then the rest of them, I am going to keep them. So let me just keep the rest of them, these guys that are not still there. So I'm going to copy paste them. And okay, we should be all set. So there you go. And just let's make sure that the additions are there as well. So don't forget about all the adds that we have. And finally, everything is ready for the final computation. Okay, so what are we seeing here? Well, this S can go to the other side, simplify the whole process, and therefore that leaves us with S equal. And don't forget that in our original formula, so in what we had before, an is equal to 2 to the n minus 1 a time plus s. So I'm just computing the s portion. That's what I'm trying to do. So s equal, which is almost the end, the final process of the computing everything here. S equal to 2 times 2 to the power n, so 2 to the power n plus 1. And then, so we took care of this s to, we take it to the other side, subtract it from 2s. The rest of the process here is super straightforward. Let's also move the negative 2n to here before I forget. So that's the negative 2n we have at the very end. And the only thing that is remaining is computing this very simple geometric series or summation. So we have a finite geometric series or sum in which obviously initial term is just 2 to the power 2. Common ratio, which means what number we are multiplying each term to the next term, is just 2. So 2 is common ratio of the geometric sum or series. And the final term is simply 2 to the n minus 1. So final term of this geometric series. Well, for the geometric series, we know that there is a famous simple formula to compute the equivalent value, which says is final term times common ratio r, so the common ratio r, minus initial term divided by r minus 1. So in this case, if you compute that, obviously denominator r minus 1 is just 2 minus 1 because common ratio is 2. So And therefore, we don't write denominator anymore. Numerator in final term times r is 2 to the n minus 1 times 2, which is 2 to the n. And then initial term is 2 to the 2. So it's just minus 2 to the 2. Okay, great. That's the, so what I found here is basically the answer for all those, the finite geometric series we have. Therefore, in conclusion, I found that S is equal to 2 to the n plus 1 minus 2 n, and don't forget about these guys, plus 2 to the n, and then minus 4. Okay, but what should we do with this? Well, we are done, because we found S, but then an is simply, I'm going to copy paste, and we are done. To be able to see it, I'm going to copy paste it here right on top. So we know an is 2 to the n minus 1 plus a1 plus s. But then we just found this. So I'm going to copy paste. I'm going to copy paste this value we just found. Here, and I'm going to use it. So therefore is equal to, okay, is equal to this value, which we know what it is. A1 is 6. So let's keep it now. A1 is 6. Okay. A1 is 6. So I'm going to use that times 6. And then we have plus the rest of them. Instead of S, substitute these guys. If you simplify the whole process, we are done clearly. Reason for that is, look what we have. So we found the value for an, and let me clearly show that. There you go. We found the value for an, and we have clearly here this component, which is matching this guy. We have minus 4, which is matching this minus 4. And then 6 times 2 to the n minus 1 plus 4 times we have 2 to the n minus 1. And then we have what we wanted. So 2 to the n. If we sum up these values, so if we sum up 2 to the n with 2 to the n plus 1 with 6 times 2 to the n minus 1, we will get 6 times 2 to the n. That is what I wanted to show. All right, so with that, we finally managed to prove the famous formula here for the closed form formula of the general term of this sequence using forward substitution, which was basically required using a little trick to figure out the value of this finite series or summation we had in the process, which we used a little trick, as I said, by multiplying s with 2 times and recompute, and then finally figure out that the value of this series or sum is s equal to what is reported here. And then we used it to find the final answer. I hope this example is helpful. Thanks for watching.